Taking a look at 4.3, dealing with patterns and nonlinear functions. So far, we've seen a few of these functions where they look like straight lines, where if we see a nonlinear function, on the other hand, it's not a line or part of a line as far as how it's graphed. So for example, these three seen here are considered linear functions because they have a straight, consistent pattern to them, even if they're dotted or just a flat line. And in comparison, we see nonlinear functions like parabolas, cubic functions, absolute value functions like y equals x squared, y equals x cubed, and the absolute value of x. So these are considered nonlinear because these at some point, although they look as if they have a consistent pattern, they kind of twist and then go in some other direction. This looks linear, but then it bounces back based off of hitting this axis. So we say that this is a nonlinear function. As far as the function seen here, this is showing the number of centimeters for a function and comparing inches to centimeters, so a conversion of sorts. And we're being asked to decide if the function is linear or nonlinear. So as we see here, we see that each inch is denoted here for 1, 2, 3, and 4 inches. The equivalent forms of the centimeters are there also, starting with 2.54, then going up to 5.08. So we see that there's a pretty consistent increase here of 2.54. We see this again, we see this again. So what do you think? Is this linear, making a straight line, or is this nonlinear? Hopefully you're saying that this is linear. It's consistent. It is moving and adding 2.54 every time. So we're totally able to say that this is linear. That being said, we might come across some examples where we have to think a little bit more strategically about what's going on. It won't be as easy. So as we see here with this table, where x values are 1, 2, 3, and 6, outcomes are 6, 3, 2, and 1. We're being asked to decide if the function's linear or nonlinear. So we have a few ways that we can do this. We have the option to graph the points out and see if they're going to be linear. So we'll try that first. So when x is 1, the outcome's 6. So that's about here. Make that there. So this is 1, 6. 2, 3, that's another point we could graph out, just about here. 3, 2, that's about here. 6, 1's about here. And so I think it's pretty easy to spot how this is definitely going to be nonlinear. Why do you think that this is nonlinear? I know I just told you it's nonlinear, but why do you think it? What makes you think that? Well, I mean, look at this. If you try to make this a straight line, it's not going to happen. It's curving, and you see it pretty quickly. So we could also denote this based off of the table. So if we look at the table and denote the changes seen here, we see a jump from 6 to 3, which is deducting 3. 3 to 2 is deducting 1. 2 to 1 is deducting 1. And we also see the changes in x, where from 1 to 2, this is just adding 1. From 2 to 3, this is adding 1. From 3 to 6, this is adding 3. So these changes are kind of all over the place. And that kind of makes sense to say that it's nonlinear because these changes aren't consistent. Although the x values are independent, the y values don't really match up as far as how those changes should work. Because even if we were changing from 1 to 1, this would have to be a consistent change also over here of subtracting 3, but we see that that's not the case. So you could base it off of these two changes, say that this is collectively nonlinear because the change is not consistent. There you go. We can also see more of the same. This one's already graphed out, so the graph, that's already done. We'll also start to piece together if we can make an equation out of this. So let's first take a look at this when it's graphed out. This looks as if it's going to make a straight line. So we can assume that this is most likely linear. We can also use the table to make sense of this, because if we look closely, we have x terms, we have y terms. So if we mark up these changes, 3 to 5, we would have to add 2. We would have to add 1 here to go from 5 to 6. To go from 6 to 9, you would have to add 3. Okay, that's fine. But let's look at the changes in x. So from 6 to 8, this would have to add 2. 8 to 9, add 1. 3 to 9, 9 to 12, add 3. And so we can denote this rate of change, how this is consistently changing, by taking our change in y. So whatever the change was for y, and divide it by the change in x. We can see how this is going to change. So for this first one, the change in y was 2. If we divide this with the 2 from over here, this is going to be consistent with that next change of 1 over 1, which is also 3 over 3, seen here and here. So collectively, we could say that our rate of change is just going to be this simplified, which is just 1. So this is saying that as we move along, every time we're adding 1, we could go backwards to figure out what these other points are going to be. So we could go here to get that 5, here again, here again. You can start to just sketch out the rest of this. But you could also mark this up with the table too. That's another option you have. But you know that your change is going to be plus 1. So you could start to say y equals positive x. And if you eventually work all the way back here, let's try this out, where if we're going back to 0, trying to find our y-intercept, we keep dragging this along, trying to make sense of it. That'll get us here. We go, this will get us to 2. This will get us here. So this is really just x, and then our y-intercept's minus 3. So there's a consistent change if we keep going over. But as we work backwards, our y-intercept's going to be negative 3. And it makes sense, because if we take all of these values, like think if we had our outcome is going to be, let's say, 6, and if we deduct 3, then the outcome has to be 3, which matches the 0.63. And we could do that for the others if we wanted to. So, makes sense to me. We'll see that we can also come across different types of equations that we create, where we'll see consistent changes. So what's going on here, similar to what we just did, we were taking differences. So if we have a consistent first difference, this is going to be a consistent line, like y equals x. If the second differences that we take are consistent, it could be a parabola. If we take a third difference, it could be cubic. So let's see what's going on here. So we're being asked to decide if these are going to represent a function. What's the rule that represents this function? So we see that there's a consistent change in the x values here of just adding 1 to the previous value. What's the change with this first one here from this 1 to 8? Well, 1 to 8, we would add 7. From 8 to 27, we would add 19. 27 to 64, 37. 64 to 125, we would add 61. So we don't see a consistent change yet. So it's definitely not linear. But we soon see, if we keep going, the second differences from 7 to 19 would be 12, 19 to 37, 18. So nothing consistent yet. But we soon see that this is going to be cubic. So this is cubic because the cubic difference, the third difference, is consistent. So we're allowed to say that this is x cubed. Sometimes you might have to add a number here or subtract a number, but you have to use your best judgment on that. What do you think for this next set? Try this out. What's the change from 5 to 9? 9 to 11. Should be saying 4, 2, 4, and 6. Go again. Go again. This one's kind of a weird one, but you would eventually see that if you take the change in y over the change in x, these are all consistent. So although the change in y was 4 over this 2, because the change in x was 2, you could say that this is a rate of change of 2. But to get that 1, you would kind of work backwards to decide on what the starting point is. So kind of weird how these examples work.